third portion wherein we are going to discuss ensembles, Liouville's theorem, Stirling's approximation, thermodynamic probability, division of a phase space into cells, and then we shall deal with the Maxwell's-Boltzmann's distribution law, which is a kind of classical law. As regards to ensembles, we shall refer to a single particle as a system. These are our new definitions. These are new keywords we are going to coin, and then we'll be talking subject in terms of these keywords. So single particle we shall call a system. A collection of particle as assembly. So after system we have a term assembly. A collection of large number of assemblies we shall call ensembles. Now I anticipate that you got to know what are ensembles. Ensembles, which are identical in features like volume, energy, total number of particles, are referred as. These elements, though identical in macro states, differ from one another in terms of coordinates and momenta, that is microstates. Elements do not interact, they behave independently, and their independence will then classify the types of ensembles. Thus, we can have a technical definition of ensemble. Ensemble is a collection of a large number of assemblies which are essentially independent of one another but macroscopically made as identical as possible. These ensembles are macroscopically made as identical as possible. The meaning of the term as identical as possible is characterized by a set of microscopic parameters which uniquely determines the equilibrium state of. In an ensemble system plays the same role as non-interacting molecules in gas. The macroscopic identity of an assembly can be achieved by choosing same set of macroscopic parameters. These parameters are uniquely determined by the equilibrium state of the system. Rather, this parameter uniquely determines equilibrium state of the system. Now, ensembles are classified into three categories: microcanonical ensembles, canonical ensembles, and grand canonical ensembles. Let us deal one by one. Microcanonical ensemble, a collection of independent assemblies having same energy, volume, and number of systems. Systems means particles, number of particles. So E, V, and N are conserved, and we have a collection of independent systems. Now all these systems, which are identical, individual, separated by rigid, impermeable insulated walls, form a microcanonical ensemble. Now we shall represent that with a picture. The most important thing about microcanonical ensemble is that we cannot specify energy of such a system exactly. So we have partitions. These partitions are formed by rigid, impermeable insulated walls. Impermeable means there is no transfer of particle from one cell to another cell. They are insulated means there is no transfer of energy and temperature. Now consider a closed system for which total energy H, which is function of QP, is equal to E, remains constant according to the equation where energy is function of position and momentum, and this energy remains constant. The locus of phase point having equal energies in phase space is called as energy surface or ergodic. It is important to note that rho is function of energy, which we have already covered, and rho remains constant. The density statistical equilibrium in the statistical equilibrium, the density in the energy shell, E to E plus dE remains constant. The second kind of ensemble we have is canonical ensemble. Canonical ensembles are collection of essentially independent assemblies having temperature, volume, and number of systems remaining same. To assure same temperature, internal thermal conduct is permitted so that equilibrium is attained and the temperature of the system remains the same. Canonical ensembles can exchange energy but not particle. Migration of particle from one cell to another cell is not. So here we have cells which are in the impermissible rigid wall, and the internal cells are permitted to have thermal conduction. They are supposed to exchange energy, but there is no feasibility of migration of particle from one cell to another cell. That kind of ensemble we are referring as canonical ensemble. Then the third and the last ensemble is grand canonical ensemble. This is very important from practical point of view. In some chemical processes, the number of particles varies as a part of physical situation in the problem. For example, radioactivity, the disintegration takes place. Such an ensemble in which exchange of energy as well as particles takes place with heat reservoir is called as grand canonical ensemble. A collection of independent assemblies having same temperature, volume, and chemical potential. So in this type we have T, V, mu, that is remaining constant. So we have ensemble which is made up of large number of cells which are essentially independent cells, and what is preserved in these cells is T, V, mu. For F degrees of freedom, we are interested in defining density of distribution. The term density of distribution is nothing but the probability distribution or distribution function. And in statistical mechanics, we refer that as rho. And this rho is function of position, momenta, and time. The volume element in such a hyperspace will be product of elemental variations in all position coordinates and all momentum coordinates. Therefore, del Q1 into del Q2 into del Q3 and so on up to del QF, where F is the degree of freedom, into del P1 into del P2 and so on up to del PF. The number of del N systems will be rho times the hyperspace del tau. Now, to obtain the total number, we will have to integrate over this phase space, and the integration first way of representing is summing out all volume elements and then representing the summation in terms of integration, where one integration rolls over the coordinate and the another integration rolls over moment. Rho upon n, this is an important quantity which is probability per unit extension in the phase space. You can call probability density in terms of number. The mean values we define in the similar fashion as integration from minus infinity to infinity. The mean value, for example, we are calculating for position x. So x times nx dx divided by integration nx dx. So integration in the denominator talks about the total number of Liouville's theorem. I shall make a passing remark on this theorem. We are not interested in deriving this theorem as it is not part of the undergraduate curriculum. However, it talks about some conservation. So from that point of view, I feel that it is important. Q dot means time derivative. Whenever a physicist puts a dot on a letter, it means d dt, that is time rate of change. So position we are differentiating with respect to time, that makes a velocity kind of component. So qi dot is equal to del h by del pi where H is Hamiltonian of a system and Pi dot is minus del H by del Qi, the equations that represents trajectory of Hamiltonian motion, and the Hamiltonian is function of all position coordinates and momenta coordinates. If we have f degrees of freedom, then we have two f variables on which Hamiltonian depends. Del rho by del Qi into dQi by dt plus del rho by del Pi into dPi by dt equal to minus d rho by dt. This is what we are referring as Liouville's theorem. Here d rho by dt represents a rate of change of density. Here there is a typographical mistake, that del rho by del Pi, that is partial derivative of the density of states with respect. Now Stirling's approximation, the calculation of n factorial becomes really cumbersome whenever the number n is large to the extent of Avogadro's number. So n factorial by definition is n into n minus 1 into n minus 2 and so on. The last number will be 1. So we can write it in reverse order, that makes a better sense, and then perform log on both sides. Log of n factorial will be log of 1. All these multiplications will be converted into addition because of the logarithmic function. Log of 1 plus log of 2 plus log of 3 and so on up to log of n. So log of n factorial will be summation log m, where m rolls from 1 to n. Now we can replace the summation sign by integration sign, and let us make a function log as function of x dx. X rolls from 1 to n. Now this is a function to be integrated by integration by parts, and let us consider 1 in multiplication with this log of x, and that 1 is a second function. So first integration log of x will be x log x minus x. So substituting limit, we have log of n factorial as n log n minus n. We have substituted here upper limit minus lower. Now we shall discuss the thermodynamic probability. In the first part we have discussed probability at large, and here I am interested in defining the thermodynamic probability as it will be required in the derivation of Maxwell's Boltzmann's. Now let us consider that we have two phase cells. We shall name first phase cell as I and another as J. And then we have 4 particles. So these 4 particles can be distributed in 2 cells as no particle in the I phase cell, all 4 in the second phase cell, that is J. So you can make such 5 combinations: 0, 4, 1, 3, 2, 2, 3, 1, 4, 0. So these are 5 macro states. Now let us consider this particular state in which in the phase cell I we have 3 particles, and in the another phase cell we have only 1 particle. Now for distinguishable particles we can have 4 substates which we call as microstates. So if we refer the particles as A, B, C, D, 4 particles are named as A, B, C, D. So A, B, C in the first cell, then A, D, B, A, C, D and B, C, D. So we have 4 microstates. So the number of microstates for a corresponding macrostate we shall define thermodynamic probability, and in this particular case it is 4. So let us make a technical definition of thermodynamic probability as a number of microstates corresponding to, in general, for n phase points, the thermodynamic probability can be expressed as W equal to n factorial upon n1 factorial into n2 factorial into n3 factorial and so on. Now N1, N2, N3 are the number of phase points in the cells 1, 2, 3 respectively. Now, taking log on both sides, we have this basic equation is in the recap: log of n factorial minus summation log of ni factorial. So here the multiplicative part is converted into addition, and this summation is fairly representing that. Now using Stirling's approximation, we have log of n factorial equal to n log n minus n minus inside bracket ni log of ni minus. Here these two terms will be cancelled because summation of all particles will lead to the total number of particles, and that will be cancelled. So log of w is equal to n log n minus summation I rolling from 1 to n ni log ni. Now taking differentiation on both sides, n being a constant, a number, total number that remains fixed throughout the consideration, so its derivative will be 0. So first part will vanish, and in the second part we have minus summation del of ni log ni. So we'll have to operate the derivative by chain rule. First function into derivative of second, log of ni derivative will be 1 upon ni, and ni will be cancelled, will be left with only 1 plus log of ni into del ni. So del ni you can take common inside bracket, you have 1 plus log ni. For maximum probability distribution, this del log of w should vanish. For any function to have a maxima, its first derivative must vanish. That provides you a condition, and the condition appears like this. We shall be exploring this in the statistics, all statistics that we are developing. Division of a phase space into cells. Let us suppose that we consider a system and we have f degrees of freedom for that particular system. So 2f dimensional phase space will correspond to that physical system, and the volume element d tau can be expressed as the product of all elemental variations for all coordinates which are f in number, and all momentum coordinates which are also again f in number. So del qf into del pf equal to h cross will be for one pair. We have such f pairs. So this product by Heisenberg's uncertainty principle will be h to the power. So number of cells n will be equal to d tau upon h to the power f, because h to the power f will be the volume of one particular smallest possible cell. Now friends, we are in position to discuss the Maxwell-Boltzmann's distribution law, which is based on classical mechanics. So this is also called as classical MB distribution law. Here we are going to deal with identical particles, but they are distinguished. To complete our discussion, let us discuss thermodynamic probability of one small system, and then we'll generalize our problem. Let us suppose that we have 4 particles to be placed in the first energy level E1. The number of particles to be placed, let us call that N1 equal to 4, and these 4 particles are identical but distinguishable. So I shall name them A, B, C and D. Let N2, we have 2 E and F particles to be placed in energy level E2. Then in N3, we don't have a particle, 0 particles to be placed in energy level E3, and in 4th energy level we would like to place 3 particles. We'll extend the name GHK to be placed in energy level E4. In the 5th energy level, let us suppose that we want to place 1 particle, and we shall extend the name L to that particle. In all, we have to accommodate 4 plus 2 plus 3 plus 1 equal to 10 particles. So capital N, we can raise summation Ni from 1 to 5. We have 5 sets, 5 energy levels in which we are placing respectively 4, 2, 0, 3 and 1. So the whole scenario is that we have to place these particles in the given energy spectrum. Let us do it practically like a game. Let the first particle is placed in the energy spectrum, and we have total 10 locations, total n locations, and in how many distinct ways we can place this particle will be obviously n distinct. Now if we like to place second particle in the energy spectrum, we are left with n minus 1 seats, n minus 1 positions. So second particle can be placed in n minus 1 distinct ways. Similarly, the third particle can be placed in n minus 2 distinct. So you can go on raising such a situation. So as we wanted to place 4 particles, let us consider fourth particle is being placed, and it will be placed in n minus 3 distinct. Now the total number of ways in which 4 particles can be placed will be n into n minus 1 into n minus 2 into n. Here, this if we write in terms of a compact formula, it will be n factorial upon n minus 4 factorial. Naturally, from the numerator, when we raise this n factorial up to n minus 3, and n minus 4 factorial upon n minus 4 factorial will be cancelled, and we are left with the number which is on left hand side. But friends, it is important to note that 4 particles can be placed in even in 4 factorial different ways. Now the placing may not differ for 4 factorial ways. So technically we have to avoid 4 factorial means 24 ways, because that doesn't make a distinct way of distribution, because particles are identical. So we are now interested in how 4 particles can be placed in even energy level in distinguishable different ways. We want to skip those identical ways in which we are distributed. So here we have to divide the last equation by 4 factorial, and we arrive at the combination formula. And in the early lectures on probability, we have concluded that NC4 will be the way of distribution. I am just revising that in a different way so that students can gather the information in a more appropriate way. So NC4, NCN1 can be the first way. So this discussion we shall generalize. Let us suppose that we have n1 number of particles that can be placed in distinct different ways in energy level E1, and these distinct different ways we shall represent by a letter P1. So P1 can be NCN1. Now N2 particles are to be placed in E2 energy level, and these can be placed in P2 distinct different ways. And while doing so, in the second step, we do not have n seats available. How many seats we have available? N minus n1. So our combination formula will be n minus n1 C n2. So in every step, we have decreased number of positions available for distribution, unlike in the first case. So let us work out it for the third case. N3 identical particles can be placed in distinct different ways in E3 energy level is suppose P3, and that P3 will be represented by N minus N1 minus N2 C N3. Here there is a mistake in the formula, that here N3 is appearing here. The correct formula is N minus N1 minus N2 C N3. So we have to work out it together. So the thermodynamic probability P together, I mean joint probability, will be by product of individual probabilities, and obviously P will be equal to P1 into P2 into P3 and so on up to Pn. because we have small n number of energy levels. So here we can represent that using a combination formula, and if we explore that combination formula, now let us reconsider this. N3 particles are being placed in distinct different ways in E3 energy level, and that probability P3 is equal to n minus n1 minus n2 C n3. Here the total probability, which represents the distinct ways in which n1 particles can be placed in E1 energy level, n2 particles can be placed in E2 energy level, and so on. That total probability will be P1 into P2 into P3 and so on up to Pn. This is a joint probability issue. We are talking about the simultaneous distribution. So this P1, P2, P3, this product can be represented by combination formula NC N1, N minus N1 C N2, N minus N1 minus N2 C N3 and so on. We have the expanded version of the combination formula. The first element NC N1 will be n factorial upon n1 factorial into n minus n1 factorial. Similarly, second element n minus n1 C n2 will be n minus n1 factorial upon n2 factorial into n minus n1 minus n2 factorial, and so on. It is interesting to see that you have similar terms in the numerator and denominator which are consequently appearing, and you can cancel them together. So you have p equal to n factorial upon n1 factorial into n2 factorial into n3 factorial, and so we can represent that p, that recap equation is appearing here. Now we are thinking the situation in a different way. Let us suppose that Gi is the probability of locating a particle in certain energy level Ei. We are directly talking about probability Gi of locating one particle in certain energy level Ei. Then the probability of locating two particles will be Gi into Gi, composite probability, joint probability, which is product of probabilities. And for two particles we have Gi square. If we have three particles, it will be Gi to the power 3 and so on. Now we will generalize it for locating Ni particles in Ei energy level. So it will be Gi into Gi into Gi Ni times. So Gi to the power Ni will be that quantity. So the total thermodynamic probability will be capital P into Gi to the power Ni. Capital P is recap equation Ni factorial upon Ni N1 factorial into N2 factorial and so on. So the final formula for thermodynamic total probability, total thermodynamic probability, W is equal to N factorial into multiplicative summation rolling over I, Gi to the power Ni divided by Ni factorial. So recap equation, look at the recap equation. We are interested in finding the maximum probable distribution for W. This is a clumsy formula for differentiation. We shall make it differentiable by operating log on both sides. Log of W will be equal to log of N factorial plus the multiplicative summation will be replaced by regular summation, log of Gi to the power Ni. So Ni will be in the multiplication, Ni log of Gi minus log of Ni factorial. So we have to explore the Stirling's approximation formula. Log of n factorial will be n log n minus n plus summation Ni log of Gi minus, inside the bracket you have to operate log of Ni factorial. So inside the bracket it will be Ni log Ni minus Ni, and when you operate minus on the elements in the bracket will be minus Ni log of Ni plus Ni. So here you have to identify the identical terms for cancellation, because summation Ni will give you total number of particles, and one with plus and another with minus will cancel the things. So log of W is equal to n log n plus summation Ni log of Gi minus Ni log of Ni. The condition for most probable distribution will be derivative of log of W equating to 0. So that's the maxima condition. So we shall first find out the derivative, and then we'll equate that equation with 0. That will offer us the condition for most probable distribution. Now let us operate del on both the sides, and log of w we are treating 0 so that we can have most probable distribution. So on left hand side we have del operated on n log n, and then summation del operated on ni log gi minus ni log ni. Here n is a fixed number, capital N is a fixed number, so derivative of a number, a constant number, will be 0. Then summation del ni, we can write del summation ni, and summation ni we can write derivative of capital N, that is a fixed number. Employing these two results, we have last equation looking as del ni log of gi is equal to log of gi into del ni. First term we have worked out. Second term ni log ni, we have to employ the chain rule. First function into derivative of second plus derivative of first into second function. Derivative of log of ni will be 1 upon ni, and derivative of ni will be del ni. So employing that, we have finally summation log of ni into del ni. So del log of w will be appearing as log of gi minus log of ni whole stuff multiplied by del ni, and the summation is to be worked out from for I ruling for all particles. So subtraction of logarithmic terms can be written as division and then operated by log terms. So log of gi upon ni into del ni. So this term we are equating to 0. This is the interesting thing we have found out, and we have two more interesting things, and we have to consider them as well, so that the equation that we are solving encompasses all points that we are considering for MB distribution. So summation log of gi upon ni del ni is equal to 0. Del ni summation is equal to 0, that we have discussed. Now ni is the number of particles in energy level EI. So ni into EI will be energy of all particles in ith energy level, and if we sum up for all energy levels, that will give us total energy E, and derivative of the total energy E, which is a constant quantity, will be 0. So we have that interesting third version, summation EI del ni equal to 0. Now we shall explore these three equations together by Lagrange's method, and we call that in the literature as Lagrange's method of undetermined multipliers. Later on we shall use physical situations again to find out the multipliers. So we have to multiply del ni summation by alpha and summation ei del ni by beta, and equate it with the first equation. So collectively we can write that summation log of gi upon ni minus alpha minus beta ei whole thing multiplied by del ni when summed for all particles. So here we are almost done, except the fact that alpha and beta are. Now let us simplify this. Log of gi upon ni is equal to alpha plus beta ei, and if we like to represent the same equation in terms of ni, it will be ni equal to gi into e to the power minus alpha minus. Now both the important equations are in the recap slot, and we are now interested in finding the multipliers. Let us begin the business with beta finding. We know entropy, Boltzmann's entropy relation, S is equal to K log W. We have discussed in our earlier video. And if we differentiate this equation, del S will be K del log of W. Now substituting del log of W from our equation, which is log of gi upon ni del ni, that is equal to summation alpha plus beta ei del ni. You refer to the last slide, and we have the quantity for del log of w. Substituting that, del s will be equal to k times summation alpha plus beta ei del ni, and we can write k alpha constant into summation del ni plus k beta into summation ei del ni. Now summation del ni is equal to 0, and summation ei del ni, that is the energy of the all particles in ith energy level, we can call internal energy, and if we sum for all energy levels, that will give us the total internal energy of the system. So our equation del S becomes K beta del U. So this is an important equation. We have on left hand side entropy, variation in entropy, and on right hand side we have variation in internal energy of the system times K beta. We shall explore first law of thermodynamics. Our last equation in the recap slot. Our last equation is in the recap slot, which is del S equal to K beta times del U. Now, the first law of thermodynamics is the conservation of energy. If dq is the amount of energy supplied to the system, it is used to raise the internal energy of the system, and rest part appears as work done. If there is no work done dw is equal to p dv. If there is no change in the volume we are considering, then dw will be 0, and dq equal to du, amount of energy supplied, appears as the rise in the internal energy of the system. This is first law that we are going to use. Second law of thermodynamics talks about the entropy. Entropy of the system is always increasing. If we consider isolated system, the entropy will never decrease with. There is an extension to that. The entropy of the system and its surrounding can remain constant in ideal cases where the system is in thermodynamic equilibrium or undergoing a fictitious reversible process. So even in the reversible processes, the entropy will not decrease, it will remain constant. dq is equal to T ds is the mathematical version of that, and here we shall combine first law of thermodynamics with second law in the sense that we shall replace dq by du. So du is equal to T ds, or ds is equal to du upon capital D. However, in the last version, in the last slide, we have calculated ds is equal to k beta du. Now we have two equations. One is coming from the discussion of Maxwell's-Boltzmann's distribution law, and another is coming from first and second law of thermodynamics. Let us compare them together and rewrite du upon T is equal to K beta du, and you can cancel du on both sides, and you can obtain beta is equal to 1 upon kt. So we have evaluated beta. Let us now strive to find out alpha. Ni, that is number of particles in energy level ith energy level, we shall write NEDE. It means that NEDE is the number of particles in the energy range E to E plus DE. DE is the variation around the central energy E. GEDE, GI we are replacing by, and GEDE represents number of unit cells in the energy range E to E plus DE. And our equation NEDE we can write as GEDE into e to the power minus alpha minus beta EI. In the earlier video, we have worked out GEDE as 2 pi v upon h cross cube 2m to the power 3 by 2 under root e. We shall combine these two equations to write NEDE. that is equal to 2 pi v upon h cross cube 2m to the power 3 by 2 under root e to the power minus alpha minus beta e. Now we shall use the normalization condition that NEDE is the number of particles in the energy range E to E plus DE. If we integrate that quantity over all possible energy levels, that is energy rolling from 0 to infinity, that will give us the total number of particles. This is normalization condition. Now on left hand side, if we integrate from 0 to infinity, we have capital N, and on the right hand side the same equation that we have. Now we have that equation in the recap, and we have taken out the constant terms out of integration sign, and the left integration is a gamma function, and under root e to the power minus beta e dE for limits 0 to infinity will be under root pi upon 2 beta to the power 3 by 2. You can refer to the gamma function, or students may remember the value of the integration, and you can substitute that value of integration in the equation. Capital N is equal to 2 pi v upon h cross cube 2m to the power 3 by 2 e to the power minus alpha, which we are interested in finding, multiplied by the value of integration, that is under root pi upon 2 beta to the power 3 by 2. Now we would like to simplify this. 2 can be cancelled. Pi into under root pi will be pi to the power 3 by 2. You can take it into the bracket along with 2m, which is having power 3 by 2. And then we have n. See, we are rearranging the equation. E to the power alpha we have on right hand side, n we are going to multiply by h cube, nh cube upon v, we have taken it to left hand side, so in the denominator, and 2m to the power 3 by 2, this quantity we are taking to the left hand side along with pi, so that is appearing 2 pi m in the denominator, and beta to the power 3 by 2 will be in the numerator, so beta upon 2 pi m to the power 3 by 2 is equal to alpha. Now we can rearrange alpha in a proper manner, and that e to the power minus alpha is referred as capital A in the literature, which is equal to nh cube upon v, 1 upon 2 pi m kt. We have substituted beta equal to 1 upon kt. So we have evaluated alpha as well as beta. Alpha is e to the power minus alpha, that is capital A. You can substitute that e to the power minus alpha, and you can rewrite the basic equation. So NED is equal to 2 pi v upon h cross cube 2m to the power 3 by 2 under root e nh cube upon v 1 upon 2 pi m kt to the power 3 by 2 e to the power minus e upon kt. So here you can cancel out certain things. H cross cube in the numerator and denominator can be cancelled. V in the numerator and denominator can be cancelled. Then 2m to the power 3 by 2 once appearing in the numerator and second time in the denominator can be cancelled, and we can recollect the things. To find NED, we are left with 2 pi n in the numerator, pi kt to the power 3 by 2 in the denominator under root e to the power minus e upon kt ge. This equation is known in the literature as Maxwell's Boltzmann's distribution law. Now friends, we shall look at this equation in terms of kinetic energy. E we shall replace by kinetic energy, and once we replace that by kinetic energy, we will be having formula for velocity distribution. We are in now position to discuss the applications of Maxwell's Boltzmann's statistics for working out various things. The distribution function just now we have derived appears on the screen. We can find velocity distribution, energy distribution. Already we are having the same equation in form of energy. We can find mean speed, RMS speed, most probable speed using that equation, and treat all those applications that we have discussed. Now friends, we are not going to work out every fine thing in this, because we have already done that in Maxwell's velocity distribution. Now the only business that I am going to do is that NEDE formula that we shall write in terms of velocity distribution. Once it resembles with Maxwell's velocity distribution, we have already discussed all the things. So same derivations can be used once we make same formula as Maxwell's velocity distribution using Maxwell's Boltzmann's distribution law. So E is equal to 1 by 2 mv square. Under root of E, we are performing under root on both sides. Under root V square will be V, so I am taking it out of the under root sign, and in the under root sign we have m upon 2. Now dE, we are differentiating this equation, E equal to 1 by 2 mv square. dE, 1 by 2 m is a constant. Derivative of V square will be twice V, and 2 can be cancelled. We are left with mv dV. Let us replace under root E and dE from the above equations. We get the equation which is appearing on the screen, and if you rearrange that equation, we are left with 4 pi n m upon 2 pi kt to the power 3 by 2 e to the power minus mv square upon kt v square dV. So here the right hand side, which is outcome of NB statistics, exactly resembles with Maxwellian velocity. Maxwellian velocity distribution, I would like to comment, we have derived without statistical mechanics. We have derived Maxwellian velocity distribution based on two axioms, two postulates, and the kinetic theory of gas. So here, as this equation resembles with Maxwell's velocity distribution, the subarticles that we have already discussed